Right now, at this very moment, you're living in what scientists call an interglacial period, a warm pause between ice ages that has lasted for roughly 11,000 years. But just 26,000 years ago, where you're sitting right now, might have been under a sheet of ice 2 miles thick, or perhaps a vast frozen grassland populated by woolly mammoths and saber-toothed cats. The coffee shop where you had lunch this afternoon might have been beneath a glacier that stretched to the horizon. The park where you walk your dog could have been tundra, where cave lions stalked their prey under skies filled with stars of impossible brilliance. Welcome to Sleep About Science. I'm your sleepy scientist, and tonight, wherever you are in the world, whether it's evening in London where gentle rain might be tapping against your windows, morning in Tokyo where the first light is touching ancient temples, or the middle of the night in New York where the city hums quietly below your apartment, we're exploring the last ice age on Earth. And if you drift off to sleep while listening, that's perfectly wonderful. In fact, I rather hope you do. There's something beautifully fitting about sleeping through a story of such deep geological time. Before we begin this journey into Earth's frozen past, please make yourself as comfortable as possible. Pull up your blankets. Imagine them as warm as the furs that wrapped our Ice Age ancestors around their fires. Adjust your pillow until it cradles your head just right. Let your breathing slow and deepen. And remember, this is educational content, not medical advice. If you haven't subscribed yet, you might want to, so you never miss these gentle journeys into science. There's something quite lovely about building this quiet community of curious minds around the world, all of us connected by our shared wonder at the mysteries of our planet. Now, close your eyes and imagine stepping outside your door, but instead of the world you know, you're greeted by a landscape so transformed it seems like another planet entirely. The air bites at your skin with a cold so profound it seems to have substance, weight, presence. Your breath forms clouds that hang in the still air like tiny ghosts. In the distance, where familiar landmarks should be Membius, where perhaps a shopping center or school or office building normally stands, rises a wall of white that stretches up and up until it disappears into low gray clouds heavy with moisture. This is not snow, not some temporary winter coating, but solid ice, ancient ice, ice that has been building for thousands upon thousands of years. This is not some distant polar region you're imagining. This is home 26,000 years ago. The last glacial maximum, as scientists call it with their wonderfully precise terminology, represents the most recent time when ice sheets reached their greatest extent across our planet. It's a world almost impossible to imagine from our current vantage point, sitting in our heated homes, looking out at landscapes shaped by 10,000 years of temperate climate. Yet it was this ice age world that shaped everything about the earth we know today. The courses of our rivers, carved by glacial meltwater, the depths of our valleys, gouged by moving ice, the very coastlines where waves meet shore, drawn by sea levels hundreds of feet lower than today. Let's begin this journey through time as gently as we always do, like settling into the deepest, most comfortable chair imaginable. Picture yourself sinking deeper into warmth and comfort as we explore this frozen world together, layer by layer, like archaeologists of time itself. 26,000 years ago, ice didn't just dust mountaintops or form seasonal caps on northern lakes the way we might see it during a particularly harsh winter today. Ice ruled entire continents with an authority so complete it's difficult for us to comprehend. The Laurentide ice sheet, a name that rolls off the tongue like poetry, stretched across most of Canada and much of the northern United States, reaching as far south as present day Illinois and Ohio. Imagine Chicago, that great American city of broad shoulders and wind, buried under ice nearly 2 miles thick. Ice so massive, so heavy, that it actually pressed the Earth's crust down like a thumb, pressing into soft clay, causing the land itself to sink under the weight. But the Laurentide was just one player in this global ice symphony. In Europe, the Fennoscandian ice sheet covered all of Scandinavia, much of northern Russia, and extended south to cover most of Britain and northern Germany. Picture London under ice, Paris at the edge of tundra, Stockholm beneath a glacier so thick that if you could somehow stand on its surface, the city below would be as far beneath your feet as commercial airplanes fly above our heads today. The Alps, those beautiful mountains that today attract millions of visitors each year, spawned their own ice sheet that flowed down into what is now the Po Valley of Italy. Even in the southern hemisphere, far from the massive northern ice sheets, glaciers expanded dramatically across Patagonia and New Zealand, creating mirror worlds of ice and snow. But here's what's truly remarkable about this frozen world. What makes it seem almost magical in its complexity. It wasn't created by some catastrophic event or sudden climate shift. No asteroid impact, like the one that ended the age of dinosaurs. No massive volcanic eruption, like the one that created the Siberian traps. No sudden reversal of Earth's magnetic field plunged our planet into an ice age overnight. Instead, the last glacial maximum was the culmination of a slow, stately dance between Earth and space that had been building for thousands of years, as inevitable and gradual as the changing of seasons, but playing out over timescales that dwarf human experience. The secret lies in something called Milankovitch cycles, named after the Serbian mathematician Milutin Milankovitch, who first calculated their effects in the early 20th century. These are subtle changes in Earth's orbit and rotation that occur over tens of thousands of years, changes so small that they would be unnoticeable within a human lifetime, yet so powerful in their cumulative effect that they can plunge our planet into ice ages or lift it out of them. Picture our planet as a spinning top that wobbles slightly as it circles the sun, not a perfect steady rotation, but one that varies in complex ways over long periods of time. These tiny wobbles, combined with small changes in the shape of Earth's orbit from circular to slightly elliptical and back again, and variations in the tilt of our planet's axis, affect how much sunlight different parts of our planet receive during different seasons. Around 70,000 years ago, these cosmic circumstances began to conspire in a way that would transform our planet. The northern hemisphere started receiving less intense summer sunlight, not dramatically less, not enough that anyone living through those summers would have noticed, but enough to set in motion a chain of events that would ultimately bury continents under ice. Now, you might think that winter cold would be what drives an ice age, and that would be a perfectly reasonable assumption. After all, it's winter when snow falls, when lakes freeze, when we bundle up in our heaviest coats. But you'd be beautifully, wonderfully wrong. It's actually the coolness of summer that matters most in the birth of an ice age. When summers aren't warm enough to completely melt the previous winter's snow, ice begins to accumulate, year after year, century after century, like a slow motion avalanche that takes millennia to reach its full power. Imagine a single snowflake falling in what is now northern Canada 70,000 years ago. It's a snowflake like any other Mebers six-sided, delicate, unique in its crystalline structure. It lands softly on ground where the previous winter's snow hasn't quite melted away, joining billions of other flakes in a carpet of white that in any normal year would disappear with the return of warm weather. But this year is different. The summer sun, weakened by Earth's orbital position, can't quite manage to melt all of the accumulated snow. More snow falls the following winter. Then summer comes again, but once more it's not quite warm enough to melt everything. The bottom layers of snow, compressed under the weight of new accumulation, begin to change. First, they become dense granular snow, then firm to transitional stage between snow and ice, and finally, solid glacial ice, blue and ancient and incredibly dense. But here's where the story becomes almost magical in its complexity, like a fairy tale written in physics and chemistry. As this ice sheet grows, it begins to change the very climate that created it. The brilliant white surface reflects sunlight back to space instead of absorbing it, cooling the regional temperature further. This is called the albedo effect, and it's one of the most powerful feedback mechanisms in Earth's climate system. The massive weight of the accumulating ice actually changes local weather patterns, creating high pressure systems that push storms away, making the region even drier and colder. What started as a few seasons of slightly cooler summers becomes a self reinforcing system. The ice sheet grows thicker, spreads wider, and creates its own climate bubble of cold, dry air. Within a few thousand years, a blink of an eye in geological terms, but hundreds of human generations, what began with a single snowflake that didn't quite melt has become a continental ice sheet, thousands of feet thick. The Laurentide ice sheet, at its maximum, was nearly 2.5 miles thick at its center, a mountain of ice larger than the entire continental United States. And oh, the world this ice sheet created. As you drift deeper into comfort, your body relaxing into warmth, while your mind wanders through this frozen landscape, picture the world of Ice Age North America. The ice sheet itself was not simply a flat, white expanse, like a frozen lake enlarged to continental proportions. Its surface rolled and undulated, like a frozen ocean caught in a moment of storm, carved by winds into ridges and valleys of ice that stretched for hundreds of miles. Near its edges, where the ice met unfrozen land, the margin was a dynamic, dangerous, spectacular place where house sized blocks of ice would break off and slowly melt, creating vast floodplains and temporary lakes that could appear and disappear within a single season. The sound alone must have been incredible. The constant groaning and cracking of ice under pressure, the splash of calving bergs, the rush of meltwater streams emerging from beneath the glacier like arteries carrying the lifeblood of a frozen continent. South of the ice, extending down into what are now the American Midwest and Great Plains, the world was transformed in ways both subtle and profound. The climate was not uniformly colder. Some regions were actually drier, others wetter than today, creating a patchwork of different environments that has no modern parallel. The Great Plains, instead of the grasslands that would later support vast herds of bison and eventually endless fields of wheat and corn, supported a unique ecosystem that scientists call the Mammoth Steppe. This mammoth steppe was unlike anything that exists on Earth today. Imagine a cold grassland that stretched from France across Siberia to Alaska and down into the American Midwest, a continuous ecosystem larger than the entire continent of Africa, supporting plant and animal communities that we can only dream of. The grasses were different, the herbs were different, even the soil was different, shaped by the unique climate conditions created by the nearby ice sheets. It was here, in this strange, beautiful, harsh, and wonderful cold grassland, that some of the most magnificent creatures in Earth's history made their home. Woolly mammoths, of course, those iconic giants that have captured our imagination and appeared in countless movies and documentaries, but they were just one member of an incredible cast of Ice Age megafauna. Cave lions prowled this landscape, but these weren't simply large versions of modern African lions. They were distinct species, perhaps 25% larger than today's lions, with longer legs for moving through snow and denser fur for insulation. Their roar must have echoed across the frozen grasslands like thunder audible for miles in the thin, clear air of the Ice Age world. Short faced bears, standing 11 feet tall on their hind legs, roamed the edges of the ice sheets. These massive predators weighed as much as modern polar bears, but had long legs that allowed them to run down prey across open terrain. Picture one of these giants moving across the tundra with surprising grace and speed, a hunter perfectly adapted to the vast open spaces of the mammoth steppe. American cheetahs, faster than any land animal alive today, chased prey across grasslands where the wind carried scents for miles. Giant ground sloths the size of small cars ambled through forests of spruce and fir that grew far south of their modern ranges, their massive claws designed for stripping bark and leaves from trees that had adapted to the strange climate conditions of the Ice Age world. Saber-toothed cats, with their iconic elongated canine teeth, specialized in hunting the largest prey animals. These weren't crude, primitive hunters, but sophisticated predators with hunting strategies adapted to taking down megafauna. Their famous teeth weren't just for show, they were precision instruments designed to deliver killing bites to specific points on large prey animals. Deer wolves, larger and more powerful than modern wolves, hunted in packs across the frozen grasslands. Their bones have been found in incredible numbers at the La Brea tar pits in Los Angeles, testimony to their abundance in the Ice Age world. These weren't the ancestors of modern wolves, but a completely separate species that evolved to fill the niche of large pack hunters in Ice Age ecosystems. Giant beavers, as large as black bears, built dams in the rivers that flowed from the melting edges of glaciers. These massive rodents created wetland ecosystems that supported entire communities of smaller animals, from waterfowl to fish to amphibians, adapted to the cold waters of the Ice Age world. But perhaps the most remarkable inhabitants of this Ice Age world were our own ancestors. Humans not only survived the last glacial maximum, they thrived in it. Small bands of hunter gatherers developed technologies and strategies that allowed them to live comfortably in some of the harshest environments Earth has ever known. These weren't desperate survivors eking out a marginal existence on the edge of extinction. They were sophisticated people with complex tools, beautiful art, rich spiritual lives, and deep, intimate knowledge of their environment. Picture a family group huddled around a fire in what is now southern France, 25,000 years ago. Outside their cave, the landscape is tundra, vast, treeless expanses dotted with hardy shrubs and grasses that can survive the long, harsh winters and brief, intense summers. The horizon is broken by the distant gleam of glaciers, rivers of ice that flow down from highlands covered in snow that never melts. But inside the cave, warmed by a carefully tended fire, this is not a scene of desperation or bare survival. These are people with rich, complex lives. The adults wear clothing that would not be out of place in a modern outdoor gear catalog, carefully tailored garments made from multiple layers of different animal skins, designed to provide insulation while allowing freedom of movement. Every piece of their clothing represents hours of skilled work, from hunting the animals to processing the hides to cutting and sewing the final garments. Their tools, scattered around the cave, represent thousands of years of accumulated knowledge and innovation. Stone spear points napped with incredible skill, so sharp they can cut through hide as easily as a modern steel knife. Bone needles fine enough to sew delicate seams, antler tool handles carved and shaped with both functional efficiency and artistic beauty. These Ice Age humans knew things we have largely forgotten. They could read weather patterns in the behavior of birds, predict animal migrations from subtle changes in wind direction, and navigate across vast, featureless landscapes using stars, landmarks, and an intimate knowledge of seasonal changes. They knew which plants provided medicine, which stones made the best tools, and how to find water in seemingly barren landscapes. But perhaps most remarkably, they were artists. Deep in caves, by the light of animal fat lamps that flickered like candles, they created some of the most beautiful art in human history. The caves of Lascaux, Chauvet, and Altamira contain paintings that seem to capture not just the appearance of Ice Age animals, but their essential spirit, the power of a charging bison, the grace of a running horse, the alert intelligence of a mammoth. These paintings weren't primitive attempts at representation by people who didn't know any better. They were sophisticated, artistic works by people who understood animal anatomy and behavior intimately, who could capture movement and emotion with just a few strokes of ochre and charcoal. The artists who created these works had spent their entire lives observing these animals, hunting them, living alongside them, understanding their behavior in ways that modern zoologists can only dream of. Throughout these caves are handprints, thousands of them, pressed against the cave walls in red and black pigment. Adults, children, people with missing fingers, people with unusual hand shapes, the gallery of individual humans reaching across 25,000 years to touch us. Each handprint is a message. I was here. I existed. I was human like you. These Ice Age humans developed technologies that wouldn't be out of place in a modern survival situation. They created clothing systems that could keep them warm and dry in temperatures that would challenge the best modern Arctic gear. They designed shelters that could be quickly assembled and disassembled as they followed animal herds across vast distances. They invented compound tools that could serve multiple purposes, crucial when every ounce of weight mattered during long migrations. They learned to preserve meat through freezing, drying, and smoking, creating food stores that could last through the long winter months when hunting was difficult. They extracted every possible nutrient from the animals they killed, using not just the meat but the organs, bone marrow, and even the contents of herbivore stomachs as sources of essential vitamins and minerals. But most importantly, they developed social technologies, ways of organizing their communities that allowed them to cooperate effectively in harsh conditions. They shared resources, cared for the injured and elderly, and developed complex systems for passing knowledge from one generation to the next. These weren't just survival skills, but rich cultural traditions that gave meaning and beauty to life in the Ice Age world. The children of these Ice Age families grew up with skills and knowledge that seem almost magical to us today. By the age when modern children are learning to ride bicycles, Ice Age children could identify animal tracks in snow, predict weather changes from the behavior of clouds, and navigate across vast landscapes using landmarks and seasonal cues. They learned dozens of different uses for common plants, which ones provided food, which ones could treat illness, which ones could be used to make tools or dyes or adhesives. They could identify different types of stone and knew which ones would make the best tools for specific purposes. They understood animal behavior so intimately that they could predict where herds would move during different seasons, where individual animals would seek shelter during storms, and how to approach different species without alerting them to human presence. These children heard stories around evening fires that weren't just entertainment, but complex oral libraries that preserved crucial information. A single story might contain detailed instructions for finding water during drought years, information about which plants were safe to eat during different seasons, and warnings about dangerous animals or treacherous terrain. These stories were living databases, constantly updated and refined as new generations added their own experiences and observations. The languages spoken by these Ice Age peoples are lost to us now, but they must have been incredibly rich and precise. They would have had dozens of words for different types of snow and ice, numerous terms for various stages of animal behavior, and complex ways of describing weather patterns, seasonal changes, and landscape features. Their vocabularies for describing the natural world were probably far more detailed and precise than anything in modern languages. But the last glacial maximum was not a static period, frozen in time like a photograph. Even at its peak, the ice sheets were dynamic, breathing, living things in their own way. They grew and retreated with smaller climate fluctuations, responding to changes in ocean currents, volcanic eruptions, and subtle variations in solar radiation. Sometimes, for decades at a time, conditions would warm slightly, and the ice margins would retreat hundreds of miles. Valley glaciers would shrink back into their mountain cirques, leaving behind moraines and outwash plains where pioneer plant species could establish themselves. Lakes would form in depressions created by retreating ice, creating oases of more moderate climate in the harsh glacial world. Other times, sudden cooling would send the ice sheets surging forward with frightening speed, overrunning forests and grasslands that had existed for centuries. These glacial advances could move miles in a single year, a wall of ice grinding forward with irresistible force, destroying everything in its path and creating new landscapes of till and outwash. One of the most dramatic of these fluctuations occurred around 20,000 years ago when massive changes in ocean circulation sent the climate system into chaos. A catastrophic collapse of ice sheets in North America sent so much fresh water into the North Atlantic that it temporarily shut down the great ocean conveyor belt that distributes heat around our planet. The result was a period called the Younger Dryas, when temperatures in the North Atlantic region plummeted even further, and Ice Age conditions intensified just as they had been beginning to moderate. Imagine the confusion and displacement this must have caused for both human and animal populations. Families that had lived in the same region for generations, following traditional migration routes and seasonal camps that had been used for thousands of years, might suddenly find their familiar landscape becoming uninhabitable. Areas that had been refugia pockets of relatively moderate climate where life could persist might suddenly become too cold or too dry to support the communities that depended on them. Animal populations faced similar challenges. Species that had spent thousands of years adapting to gradually changing conditions found themselves once again facing the harsh realities of deep glaciation. Migration routes that had been reliable for generations might become blocked by advancing ice or changing vegetation patterns. Some species adapted, some migrated to new territories, and some simply disappeared from the fossil record, unable to cope with the rapid changes. But it's important to remember, as you settle deeper into comfort and warmth, that even during the deepest cold of the last glacial maximum, our planet was not uniformly frozen. This wasn't a global deep freeze that turned Earth into a giant snowball. The tropics, while cooler than today, remained warm and humid. Rainforests still flourished, though they were smaller and different in composition from their modern counterparts. In what is now the Amazon basin, dense tropical forests supported communities of animals and plants that were in many ways similar to those found there today. Monkeys swung through the canopy, jaguars prowled the forest floor, and countless species of birds, insects, and plants created complex ecosystems that persisted throughout the Ice Age. These tropical refugia served as biological warehouses, preserving genetic diversity that would later spread out to recolonize areas as climates warmed. Coral reefs grew in tropical seas, though they were distributed differently due to the dramatically lower sea levels. Many of the reefs that existed during the Ice Age are now hundreds of feet underwater, drowned by the rising seas that followed the melting of the great ice sheets. Archaeologists and marine biologists occasionally discover these ancient reefs, perfectly preserved underwater monuments to Ice Age marine ecosystems. And this brings us to one of the most profound and dramatic effects of the last glacial maximum dive, the complete transformation of Earth's coastlines. With so much water locked up in ice sheets, an estimated volume equivalent to lowering global sea levels by nearly 400 feet, the geography of our planet was utterly different from anything we know today. Picture yourself standing on what is now the edge of the Atlantic Ocean, anywhere along the eastern coast of North America. During the last glacial maximum, you would have to walk hundreds of miles eastward across dry land before you reach the sea. The continental shelf, that underwater extension of the continent that today lies beneath hundreds of feet of ocean water, was exposed as rolling hills and broad plains crossed by rivers that are now submarine canyons. The Hudson River didn't end at New York Harbor as it does today, but continued for another 100 miles across the exposed continental shelf before finally reaching the Ice Age Atlantic. The same was true for every major river system in the world. They all extended much farther out to sea, carving valleys that are now drowned beneath the risen oceans. Land bridges appeared between continents, creating connections that allowed plants and animals to spread into new territories. The most famous of these is Beringia, the land bridge that connected Asia and North America across what is now the Bering Strait. This wasn't just a narrow isthmus that you could see across, but a broad landmass, hundreds of miles wide, supporting its own unique ecosystems and serving as a highway for both animals and humans moving between continents. Britain was not an island during the last glacial maximum, but was connected to continental Europe by a broad plain called Doggerland. This area, now beneath the North Sea, supported forests, grasslands, and human communities. Archaeological evidence suggests that Doggerland was a rich, productive landscape that may have supported some of the densest human populations in Ice Age Europe. Australia and New Guinea formed a single landmass called Sahul, separated from Asia by only narrow straits that could be crossed by boat. This allowed the ancestors of modern Aboriginal Australians to reach Australia at least 50,000 years ago, making them some of the world's earliest maritime explorers. In Southeast Asia, falling sea levels exposed vast areas of the Sunda Shelf, connecting the mainland to many of the islands that today make up Indonesia and Malaysia. Tigers, elephants, and orangutans could walk between areas that today are separated by hundreds of miles of open ocean. The coastlines that did exist during the last glacial maximum were dramatically different from those we know today. Rivers, swollen with meltwater from nearby glaciers, carved deep gorges as they rushed toward the lowered sea levels. These rivers carried enormous loads of sediment rock flour ground up by glacial action, creating vast deltas and floodplains in areas that are now deep underwater. Where waves broke on Ice Age beaches, the character of the coastline was often dramatically different from today. In many areas, glaciers extended directly to the sea, creating coastlines of ice cliffs where icebergs would break off and drift away. In other areas, the combination of lower sea levels and different climate patterns created vast tidal flats and shallow seas that supported enormous populations of marine life. Picture yourself standing on the edge of the last glacial maximum world, where one of the great ice sheets meets unfrozen land. This boundary, called the glacial margin, is not the clean, neat line that you might see on a map, but a chaotic, dynamic zone where ice, water, rock, and sediment interact in constantly changing ways. The ice sheet itself rises before you like a white mountain, its surface scarred by crevasses and melt channels. The ice doesn't end abruptly, but extends in a complex array of tongues and lobes that follow the contours of the underlying landscape. Some areas of the margin are stable, where the ice has been in roughly the same position for centuries. Other areas are dynamic, where the ice advances and retreats seasonally or in response to climate fluctuations. Meltwater streams emerge from beneath the ice, carrying with them rock ground to flour by the glacier's movement. These streams meander across broad outwash plains before collecting into larger rivers that flow toward distant oceans. The water is cloudy with suspended sediment, giving it a distinctive gray or brown color that marks it as glacial in origin. The ice itself tells a story of thousands of years of accumulation and movement. Near its surface, you can see annual layers, light bands of winter ice, alternating with darker bands that contain dust and debris from summer melting and refreezing. Deeper in the ice, compressed under the weight of centuries of accumulation, these layers become harder to distinguish, but they're still there, a record of ancient climates preserved in frozen form. Near the base of the glacier, the ice is filled with rocks and sediment, the debris of mountains and forests, ground up and carried along by the glacier's inexorable movement. This is called basal ice, and it's often dark brown or black from all the material it contains. When glaciers retreat, they leave behind this debris in the form of moraines, hills, and ridges that mark the former positions of ice margins. The sounds of the glacial margin are unlike anything in the modern world, except perhaps in the remaining ice sheets of Greenland and Antarctica. There's the constant creaking and groaning of ice under pressure, sounds that can be heard for miles on quiet days. The sharp crack of crevasses opening, echoing like gunshots across the ice surface. The thunder of ice falls where the glacier drops over steep terrain, and the steady drip and trickle and rush of melt water finding its way to the sea. But this is not a silent, dead landscape. It's alive with the voices of geological processes operating on a scale almost beyond human comprehension. The ice is constantly moving, flowing like thick honey under its own weight. Rocks frozen into the ice act like sandpaper, grinding against the bedrock beneath and carving the landscape in ways that will still be visible millions of years in the future. And everywhere there is life, even in this harsh environment, plants colonize the moraines and outwash plains, specially adapted to the harsh conditions and poor soils. Animals find ways to exploit the resources available in this marginal environment. Even humans, with their remarkable adaptability, find ways to thrive at the edges of the ice sheets. As you settle deeper into warmth and comfort, let your mind wander through this transformed world. Imagine walking across landscapes that no longer exist, breathing air with a different chemistry than what fills your lungs today, looking up at night skies unmarked by any human light pollution, seeing stars with a clarity that's impossible in our modern world. The animals that inhabited this Ice Age world were not just larger versions of modern species with adaptations for cold weather. They were the products of millions of years of evolution in Ice Age conditions, perfectly engineered for their harsh but productive environment. Woolly mammoths were masterpieces of cold weather engineering. Their ears were much smaller than those of their tropical elephant cousins, reducing heat loss. Their trunks had special adaptations that prevented freezing, including a complex network of blood vessels that pre-warmed incoming air. Their blood contained antifreeze proteins that prevented ice crystals from forming in their circulatory systems. But perhaps most remarkably, mammoths had a two-layer hair system that rivaled anything modern textile engineers have devised. The outer layer consisted of long, coarse guard hairs that could be up to 3 feet long, providing protection from wind and precipitation. Underneath was a dense layer of soft, woolly undercoat that provided incredible insulation. This hair system was so effective that mammoths could maintain their body temperature in conditions that would quickly kill most modern animals. Their feet were specially adapted for walking on ice and snow, with thick pads that spread their weight and prevented them from sinking into soft surfaces. Their tusks, which could grow to incredible lengths, were used not just for fighting and display, but for digging through snow to reach the grasses and herbs beneath. But mammoths were more than just well adapted individuals. They were ecosystem engineers, animals that shaped the very environment they lived in. Their feeding behavior helped maintain the mammoth steppe grassland. They knocked down trees and shrubs that tried to colonize the grasslands, preventing the establishment of forests that would have changed the entire character of the ecosystem. Their massive feet, as they moved in herds across the landscape, created a trampling effect that helped maintain the soil conditions that grassland plants preferred. Their dung provided fertilizer that enriched the soils and supported the productivity of the grassland ecosystem. When mammoths disappeared at the end of the Ice Age, the ecosystem they had helped create disappeared with them, replaced by forests and tundra that were far less productive. Woolly rhinoceros shared the mammoth steppe with their more famous elephant cousins. These weren't the ancestors of modern rhinos, but a completely separate lineage adapted to cold conditions. They had thick, woolly coats and a distinctive horn arrangement, a large front horn and a smaller rear horn that was perfectly designed for sweeping snow away from vegetation. Giant deer, known to scientists as megaloceros, roamed the edges of the ice sheets with antlers that could span 11 feet from tip to tip. These incredible structures weren't just for show pests, they were complex signaling devices that could communicate information about the health, age, and genetic quality of their bearers across vast distances. The energy required to grow such enormous antlers meant that only the healthiest, most successful males could support them. Cave lions, as I mentioned before, were the apex predators of the mammoth steppe. Recent genetic studies have shown that they were closely related to modern lions, but had been isolated in northern environments for so long that they had developed distinct characteristics. They were larger, more heavily built, and had thicker fur than their African cousins. But perhaps most remarkably, cave lions lived in smaller social groups than modern lions, or may have been largely solitary. This makes sense when you consider the nature of their environment. The mammoth steppe was incredibly vast, and prey animals were often widely scattered. Large prides that work well in the concentrated environments of African savannas would have been disadvantageous in the open expanses of the Ice Age world. Short faced bears represent one of the most formidable predators ever to walk the earth. These massive animals stood 11 feet tall on their hind legs and had a build that was more like a giant cheetah than a modern bear. Long legs, relatively lean body, and a skull design that suggests they were pursuit predators rather than the omnivorous foragers that most modern bears are. Recent research suggests that short faced bears may have been primarily scavengers, using their size and speed to steal kills from other predators. Their long legs would have allowed them to cover vast distances quickly, and their incredible size would have given them the ability to drive away any other predator from a kill. They were the ultimate kleptocrats of the Ice Age world. American cheetahs were built for speed in the open grasslands of the mammoth steppe. These weren't the ancestors of African cheetahs, but the result of convergent evolutions, similar environments producing similar solutions in unrelated animals. They had the same general body plan as modern cheetahs' light build, long legs, flexible spine, but were adapted to different prey and different terrain. The pronghorns that still live in western North America today are actually the descendants of animals that evolved to escape American cheetahs. This is why pronghorns can run at speeds of up to 60 miles per hour, far faster than any predator in their current environment requires. They're still running from ghosts, from predators that disappeared 12,000 years ago, but left their mark in the form of incredible speed in their surviving prey. Dare wolves were the most common large predator at the La Brea tar pits, with thousands of individuals recovered from those ancient pools. This suggests that they were highly social animals that hunted in large packs, cooperating to bring down megafauna much larger than themselves. Their skulls show adaptations for crushing bones, suggesting they were able to extract resources from carcasses that other predators couldn't access. Giant ground sloths came in many varieties, from species the size of large dogs to others that rivaled elephants in size. Megatherium, the largest of these, stood over 10 feet tall on its hind legs and weighed as much as an adult elephant. Despite their massive size, they were herbivores, using their enormous claws to strip bark from trees and dig up roots. These ground sloths were incredibly successful animals, with some species surviving until very recently in geological terms. On some Caribbean islands, ground sloths persisted until just a few thousand years ago, long after their mainland cousins had disappeared. There are even suggestions that some smaller species might have survived into historical times. Giant beavers, as large as black bears, built dams in the rivers and streams that flowed from melting glaciers. These massive engineering projects created wetland ecosystems that supported entire communities of plants and animals. The wood from Ice Age beaver dams has been found preserved in sediments throughout North America, testament to the incredible scale of their building activities. But it wasn't just the large animals that made the Ice Age world remarkable. Smaller creatures also thrived in ways that seem almost magical to our modern perspective. Arctic foxes, with incredibly thick winter coats, hunted lemmings and ground squirrels across the tundra, their fur so dense they could sleep comfortably on snow at temperatures that would be fatal to most animals. Prica, small rabbit like creatures, lived in rock piles and made hay piles to sustain them through the long winter months. These industrious little animals would spend the brief summer months cutting and drying grasses and herbs, storing them in carefully constructed caches that would provide food during the months when fresh vegetation was unavailable. Even insects had remarkable adaptations to Ice Age conditions. Some species developed antifreeze proteins in their body fluids, allowing them to survive being frozen solid during winter months. Others evolved complex life cycles that took advantage of the brief but incredibly productive summer growing seasons, timing their reproduction to coincide with the peak abundance of food sources. The plant communities of the Ice Age world were as unique and fascinating as the animals. The mammoth steppe supported grasses and herbs that today are found growing in widely separated parts of the world. It was a unique plant community that has no modern analog. You can't go anywhere on Earth today and see anything quite like it. This grassland was incredibly productive, supporting enormous herds of large herbivores. The combination of long daylight hours during the brief summer growing season, fertile soils created by glacial activity, and the fertilizing effect of countless grazing animals created conditions that allowed plant communities to flourish in ways we can barely imagine. Many of the plants that grew in the mammoth steppe were what botanists call forbs, broad-leaved herbaceous plants that were rich in nutrients and provided high-quality forage for large herbivores. These plants grew alongside various grass species to create a diverse, productive ecosystem that could support animal biomass densities that exceeded those of any modern grassland. Trees, where they could survive in the Ice Age world, formed very different communities than we see today. In North America, spruce forests extended far south of their current range, growing in areas that today support deciduous forests or even grasslands. These spruce forests were probably quite different from modern boreal forests, with different understory plants and different animal communities. In Europe, most forests disappeared during the depths of the last glacial maximum, surviving only in small refugia in protected valleys of southern Spain, Italy, and the Balkans. These refugia served as genetic reservoirs that would later provide the source populations for reforestation as the ice sheets retreated. Modern European forests are actually quite recent in geological terms, having recolonized most of the continent only within the last 10,000 years. The survival of trees in these refugia is one of the most remarkable stories of Ice Age adaptation. In some cases, entire forest ecosystems persisted in valleys that were just a few miles wide, surrounded by tundra or ice covered landscapes. These refugia were biological islands, preserving complex communities of plants, animals, fungi, and microorganisms through the harshest period of the Ice Age. Recent genetic studies of modern European trees have revealed the locations of these ancient refugia by tracing the migration routes that plants followed as they recolonized Europe after the Ice Age. It's a story written in DNA, preserved in the chromosomes of every oak, beech, and pine tree growing in Europe today. The oceans during the last glacial maximum were transformed as dramatically as the land, though in ways that are less immediately obvious to us land dwelling creatures. With so much water locked in ice sheets, sea levels dropped by nearly 400 feet, enough to expose vast areas of what is now the sea floor, but also enough to dramatically change the chemistry and circulation patterns of the remaining ocean water. The water that remained was saltier, because while water had been removed to form ice, the salt had stayed behind, becoming concentrated in the smaller volume of remaining seawater. This increased salinity affected the density of seawater, which in turn affected circulation patterns and the distribution of nutrients throughout the ocean basins. Ocean temperatures were also dramatically different from today. In some regions, sea surface temperatures dropped by as much as 10 degrees Celsius, enough to support sea ice in areas where it never forms today. The Mediterranean Sea, for example, may have experienced winter sea ice formation, creating conditions more like the modern Baltic Sea than the warm, temperate body of water we know today. Ocean currents, those great highways of heat and nutrients that regulate our planet's climate, followed completely different paths during the last glacial maximum. The Gulf Stream, that massive current that brings warmth from the tropical Atlantic to Western Europe, was much weaker than today and followed a different course. Instead of flowing northeast toward Europe, it may have turned more directly eastward, reducing the amount of heat transported to higher latitudes. The result was that Western Europe, which today enjoys a relatively mild climate despite its northern latitude based London, is actually farther north than most of Canada, experienced conditions more like those of modern Siberia. Paris would have had temperatures similar to those of modern Alaska, and even the Mediterranean region experienced harsh continental winters. In the Pacific Ocean, the different sea levels and temperatures created very different patterns of circulation and marine productivity. The Bering Sea, instead of being a relatively shallow body of water as it is today, was largely dry land. The California Current, which today brings cold, nutrient rich water south along the western coast of North America, followed a different path and had different characteristics. These changes in ocean circulation had profound effects on marine ecosystems. Many species of whales, Dolphins and seals existed during the Ice Age, but their populations and distributions were very different from today. Some species that went extinct at the end of the Ice Age lived in coastal waters that are now far beneath the surface of the sea. The changes in ocean chemistry also affected the entire marine food web, with different circulation patterns. Nutrients were distributed differently throughout the ocean basins. Some areas that are highly productive today may have been biological deserts during the Ice Age, while other areas that are relatively barren today may have supported rich marine ecosystems. Coral reefs during the last glacial maximum were distributed very differently than they are today, largely because of the dramatically lower sea levels. Many of the reefs that exist today are relatively young, having grown upward as sea levels rose after the Ice Age. The ancient reefs that existed during the Ice Age are now submerged platforms, some of them hundreds of feet underwater. Marine archaeologists and paleontologists occasionally discover these drowned reefs, which provide incredible windows into Ice Age marine ecosystems. These ancient reefs often contain the fossilized remains of corals, fish, and other marine organisms that lived in very different ocean conditions than exist today. The atmospheric chemistry of the Ice Age world was also significantly different from today in ways that affected every living thing on the planet. Carbon dioxide levels were nearly 40% lower than pre industrial levels, and even lower than the levels that existed before humans began burning fossil fuels on a large scale. This dramatic reduction in atmospheric CO2 wasn't just a result of reduced plant growth during the cold climate. Much of the missing carbon was locked up in the deep ocean, sequestered there by different patterns of ocean circulation and the increased solubility of CO2 in the cold seawater of the Ice Age world. The lower carbon dioxide levels contributed to the cold climate through the greenhouse effect. Thus, less CO2 in the atmosphere meant less heat trapped near Earth's surface. But the reduced CO2 also meant that plants had to work harder to photosynthesize. Carbon dioxide is the raw material that plants use to build their tissues, and with less of it available in the atmosphere, plant growth was limited in ways that are difficult for us to imagine. Many plant species responded to these low CO2 conditions by developing more efficient photosynthetic pathways and more effective mechanisms for capturing and concentrating carbon dioxide. The plant communities that existed during the Ice Age were often dominated by species that could function well with limited atmospheric CO2, to another factor that made Ice Age ecosystems so different from those of today. The lower atmospheric pressure of the Ice Age worlds, a result of the different distribution of air masses created by the massive ice sheets, also affected plant and animal physiology in subtle ways. Many species that lived at relatively low elevations during the Ice Age were actually experiencing atmospheric conditions similar to those found at high altitudes today. Even the night sky would have looked dramatically different during the last glacial maximum, and not just because there were no electric lights anywhere on Earth. The Earth's orbital position and axial tilt were different, meaning that certain stars and constellations would have appeared in different positions relative to the horizon. The North Star, Polaris, was not directly north during the Ice Age because of the slow wobble in Earth's axis called precession. The north pole of the sky pointed toward a region of space between stars rather than toward any bright star. Ice Age navigators would have had to use different techniques for finding north, probably relying on the rotation of star patterns around the empty north celestial pole. The position of the sun in the sky during different seasons was also different, affecting the length and intensity of daylight throughout the year. The changes were subtle, not dramatic enough to be obvious to anyone living through them, but significant enough to affect plant growth patterns, animal behavior, and human activities. Indigenous peoples around the world have oral traditions that may preserve memories of the Ice Age world, passed down through hundreds of generations in the form of stories, songs, and ceremonies. Stories of great floods that may relate to the catastrophic draining of ice dammed lakes. Tales of times when the sea was much lower, when people could walk to places that are now islands. Legends of landscapes populated by enormous animals that no longer exist. Australian Aboriginal traditions include stories of times when people could walk to places that are now separated by water, which corresponds to the period when Australia and New Guinea were connected during the Ice Age. Some of these traditions may preserve memories of events that occurred more than 10,000 years ago, making them among the oldest historical records in the world. North American indigenous traditions include stories of great ice walls and times when the world was very different, which may preserve cultural memories of the retreat of the great ice sheets. While we must be careful not to over-interpret these stories or assume that they are literal historical accounts, they may contain kernels of information about environmental conditions that are now lost to scientific investigation. The end of the last glacial maximum began slowly and unevenly around 20,000 years ago, as the same Milankovitch cycles that had caused the Ice Age began to reverse their effects. Northern Hemisphere summers began to receive more intense sunlight, and the great ice sheets started their long, complex retreat. But this was not a smooth, uniform process of warming and ice retreat. Instead, the transition from Ice Age to interglacial was punctuated by rapid advances and retreats, periods of stagnation, and dramatic collapses that sent massive amounts of fresh water into the oceans. One of the most dramatic events in this retreat occurred around 14,000 years ago, when massive ice-dammed lakes in western North America suddenly drained in catastrophic floods that were unlike anything in recorded human history. Lake Missoula, held back by an ice dam in what is now western Montana, contained more water than Lake Erie and Lake Ontario combined. When the ice dam failed, probably due to the pressure of the water gradually lifting and floating the ice, the entire lake emptied in a matter of days or weeks. The Missoula floods, as geologists call them, carved the channeled scablands of eastern Washington state, creating a landscape that looks almost alien in its starkness. Enormous coulees, dry waterfalls hundreds of feet high, and scattered boulders the size of houses all bear witness to the incredible power of these floods. The floodwaters moved at speeds of up to 80 miles per hour, carrying icebergs, boulders, and sediment toward the Pacific Ocean. But even more dramatic was the periodic drainage of Lake Agassiz, a glacial lake in central North America that at its peak was larger than all the modern Great Lakes combined. This enormous lake was held back by the retreating Laurentide ice sheet, and as the ice retreated, different drainage outlets opened and closed, causing the lake to drain and refill multiple times. When ice dams holding back Lake Agassiz failed, the resulting floods were truly continental in scale. One of these drainage events around 8,200 years ago sent so much fresh water into the North Atlantic, more water than flows over Niagara Falls continuously for several years, that it temporarily shut down the ocean circulation patterns that transport heat from the tropics to higher latitudes. The result was a dramatic cooling event that affected climate patterns around the world. Temperatures in the North Atlantic region dropped rapidly. Glaciers that had been retreating began to advance again, and the process of warming that had been gradually ending the Ice Age was temporarily reversed. As the ice sheets retreated, they left behind a landscape that was utterly transformed from anything that had existed before the Ice Age. The enormous weight of the ice sands, in some places more than a mile thick, had depressed the Earth's crust, like a person sitting on a soft mattress. As the ice melted away, the land began to slowly rise back up, a process called isostatic rebound that continues today in places like Scandinavia and the Hudson Bay region of Canada. In some areas, the land is still rising at rates of several centimeters per year, more than 15,000 years after the ice melted away. This ongoing rebound affects everything from sea levels to the flow of rivers, and it will continue for thousands of years as the Earth's crust slowly returns to its pre ice age configuration. The retreating ice also left behind a complex geography of moraines, hells, and ridges of rock debris that marked the former edges of glaciers. These moraines form some of the most distinctive landscapes in regions that were glaciated during the Ice Age. Long Island in New York is actually a terminal moraine marking the farthest advance of the ice sheet that covered New England. Cape Cod is another glacial feature created by sediments deposited at the edge of the retreating ice. The Finger Lakes of upstate New York were carved by glacial tongues that extended south from the main ice sheet, gouging deep valleys that later filled with water as the climate warmed. The Great Lakes themselves are the result of glacial action, carved and modified by the ice sheets over multiple glacial cycles. Much of the familiar geography of the northern United States and Canada was created, carved, deposited, or modified by the ice sheets of the last glacial maximum. The rolling hills of New England, the flat plains of the upper Midwest, the countless lakes of Minnesota and Wisconsin air, all of these landscapes bear the signature of glacial action. Rivers that had been dammed, diverted, or completely rerouted by ice sheets had to find new courses as the ice retreated. The Mississippi River, for example, carried vastly more water during the Ice Age melt than it does today, and its delta extended much farther into the Gulf of Mexico. The sediment load carried by meltwater rivers was enormous, creating vast alluvial fans and outwash plains that are still visible today. In some cases, entire new river systems were created by glacial meltwater. The Columbia River Gorge, that spectacular canyon that cuts through the Cascade Mountains, was carved primarily by the Missoula floods rather than by the normal processes of river erosion. The gorge was cut in a matter of weeks or months rather than the millions of years that would normally be required for such a dramatic landscape feature. As climates warmed and ice retreated, plant and animal communities began the long, complex process of recolonizing territories that had been under ice for tens of thousands of years. But this was not simply a return to pre ice age conditions. The world that emerged from the last glacial maximum was fundamentally different, shaped by the long period of glaciation in ways that would affect ecosystems for thousands of years to come. Many species had gone extinct during the Ice Age, creating ecological vacancies that would be filled by different species, or sometimes not filled at all. Other species had evolved in isolation in different refugia, becoming genetically distinct populations, or even new species by the time the ice retreated. The recolonization process created entirely new combinations of species that had never before existed together. Trees slowly recolonized the landscapes revealed by retreating ice, but the process was surprisingly slow. It takes time for seeds to disperse across large distances, for soils to develop, and for complex forest ecosystems to establish themselves. In many areas, thousands of years passed between the retreat of ice and the establishment of mature forests. The recolonization process was also constrained by geographic barriers that had been created by glacial action. Mountains, lakes, and river valleys could prevent or channel the movement of species, creating patterns of biodiversity that persist today. The genetic structure of many modern species still reflects these post glacial migration routes. Animals faced similar challenges in recolonizing post glacial landscapes. Many of the large herbivores that had thrived in the mammoth steppe ecosystem were unable to adapt to the forested landscapes that replaced the grasslands as climates warmed. Without the large herbivores to maintain them through their feeding and trampling activities, the grassland ecosystems themselves disappeared, replaced by forests and tundra that supported much lower animal biomass. The transition from Ice Age to interglacial was particularly dramatic and challenging for human populations. As ice sheets retreated and sea levels rose, the land bridges that had connected continents for thousands of years disappeared under rising waters. Populations that had been connected for millennia were suddenly isolated from each other, beginning independent cultural and genetic evolutionary trajectories. The Bering Land Bridge, that great highway between Asia and North America, was flooded around 11,000 years ago, separating Asian and American populations, just as both continents were experiencing rapid environmental changes. The timing of this flooding may have been crucial for the development of distinctly American cultures and the spread of humans throughout the Americas. Doggerland, the broad plain that connected Britain to continental Europe, was gradually flooded as sea levels rose, turning Britain into an island for the first time in tens of thousands of years. The people living in Doggerland faced the gradual loss of their homeland, probably retreating to higher ground over many generations as the sea slowly claimed their territory. But the end of the Ice Age also opened up vast new territories for human colonization. As ice sheets retreated from northern Europe and North America, humans followed close behind, becoming some of the first large mammals to colonize landscapes that had been under ice for tens of thousands of years. These were true pioneers, entering ecosystems that had never before supported human populations. These post glacial pioneers had to learn to adapt to entirely new environments, developing new technologies and social structures to survive in landscapes that were often dramatically different from the Ice Age world their ancestors had known. They learned to hunt different animals, gather different plants, and navigate different terrains. The development of agriculture, which occurred independently in several parts of the world around 10,000 to 12,000 years ago, was intimately connected to the end of the last glacial maximum. The stable, warm climates of the early Holocene hour current interglacial period provided the consistent growing seasons that made agriculture possible. The seasonal flooding patterns of rivers, which had been established by glacial meltwater and the dramatic climate changes of the late Ice Age, created the fertile floodplains where the first crops were domesticated. The Nile, the Euphrates, the Indus, the Yellow River, all of these great rivers that cradled early agricultural civilizations had their modern characteristics established by the end of the Ice Age. Many of the animals that were domesticated by early agricultural peoples were species that had survived the Ice Age in close association with humans. Dogs had been domesticated from wolves at least 15,000 years ago, probably during the height of the last glacial maximum. Reindeer had been managed by human populations in northern Eurasia for thousands of years before formal domestication. The relationship between humans and animals that began in the Ice Age world laid the foundation for the agricultural revolution that followed. Ice Age hunters had developed intimate knowledge of animal behavior, social structures, and reproductive patterns. This knowledge, accumulated over thousands of years, made it possible for their descendants to successfully domesticate wild species and develop the animal husbandry practices that became the foundation of agricultural societies. The genetic legacy of Ice Age populations persists in modern humans in ways that scientists are only beginning to understand. Recent advances in ancient DNA analysis have allowed researchers to extract genetic material from Ice Age human remains, providing direct insights into the ancestry of modern populations. These studies have revealed that we carry within our genes the story of Ice Age survival, adaptation, and migration. The genetic diversity of modern human populations reflects the various refugia where our ancestors survived the last glacial maximum and the subsequent migrations and mixing that occurred as climates warmed and populations expanded. Some of the genetic adaptations that helped our ancestors survive the Ice Age persist in modern populations. Certain variants of genes involved in cold tolerance are more common in populations whose ancestors lived through the last glacial maximum in northern regions. Adaptations related to processing high fat diets, which would have been crucial for Ice Age survival, are found at different frequencies in different modern populations. Even our immune systems bear the signature of Ice Age survival. Living in small, isolated bands during harsh conditions would have exposed our ancestors to different disease pressures than those faced by people living in large, settled communities. Some of the genetic variants that affect immune function in modern populations may represent adaptations to the specific disease environments of the Ice Age world. The psychological and cultural legacy of the Ice Age may be even more profound and harder to measure. Some evolutionary psychologists suggest that many of our instinctive fears and preferences may reflect adaptations to Ice Age conditions. Our fear of darkness, our wariness of predators, our preference for landscapes that combine shelter with open views. All of these may be psychological echoes of adaptations that were crucial for survival in the Ice Age world. Our deep emotional connections to certain animals, particularly large mammals like horses, wolves, and big cats, may reflect the intimate relationships our Ice Age ancestors had with the megafauna of their world. The cave paintings that move us so profoundly today suggest that these relationships were not simply utilitarian, but involved complex emotional and spiritual connections between humans and the animals they lived among. Even our capacity for cooperation, which is unusual among primates and has been crucial for the development of human civilization, may have been strengthened by the necessity of working together to survive Ice Age conditions. The small bands of hunter gatherers who survived the last glacial maximum had to be extraordinarily cooperative to succeed in such challenging conditions. Groups that could effectively share resources, coordinate complex hunts, care for the injured and elderly, and maintain social cohesion during long, harsh winters would have had significant survival advantages over less cooperative groups. Over thousands of generations, this would have selected for individuals and cultures that were skilled at cooperation, communication, and mutual support. As you drift towards sleep, imagine the incredible journey from that Ice Age world to our modern one. Picture the countless generations of humans who lived through the gradual warming, witnessed the retreat of the great ice sheets, adapted to the disappearance of the megafauna, developed agriculture, and slowly built the complex technological societies we inhabit today. Each generation faced the challenge of adapting to changing conditions while preserving and transmitting the knowledge and skills that had allowed their ancestors to survive. They were living bridges between the Ice Age world and our own, carrying forward the wisdom of their forebears while developing new ways of living in a transformed landscape. The story of the last glacial maximum is ultimately a story about resilience, the resilience of life itself in the face of dramatic environmental change. It shows us that our planet is capable of supporting complex, beautiful, and diverse forms of life, even under conditions that we might consider extreme or hostile by our current standards. It also provides us with a deep time perspective that is essential for understanding our planet and our place on it. The Ice Age world persisted for tens of thousands of years, longer than all of recorded human history. The warm interglacial period we currently inhabit has lasted for about 11,000 years, and based on natural orbital cycles, might be expected to continue for several thousand more years, though human influences on climate may be changing that trajectory in unpredictable ways. The last glacial maximum represents just one chapter in Earth's ongoing climate story, but it's a chapter that has profound relevance for understanding how climate systems work and how life responds to environmental change. Our planet has experienced dozens of ice ages over the past 2 million years, each one unique in its extent, duration, and characteristics. Before the current pattern of ice ages began, Earth experienced even more dramatic climate changes, including periods when no ice existed at the poles at all, and other times when ice may have extended nearly to the equator. The ice age cycles of the past 2 million years represent just the most recent phase in a much longer story of climate change that extends back billions of years. This deep time perspective doesn't diminish the significance of current climate changes, but it does place them in a broader context. It shows us that Earth's climate system is dynamic and capable of dramatic shifts. It also demonstrates that life is remarkably adaptable and persistent, capable of thriving under conditions very different from those we consider normal today. The legacy of the last glacial maximum surrounds us in ways both obvious and subtle. The Great Lakes that provide fresh water to tens of millions of people were carved and shaped by glaciers. The fertile soils of the American Midwest were created by rock ground up by ice sheets and spread by glacial meltwater. The fjords of Norway, the valleys of Yosemite, the moraines of New England, the drumlin fields of Wisconsin, all of these landscapes bear the unmistakable signature of Ice Age glaciation. But the legacy extends far beyond physical geography. The genetic diversity of modern species, the distribution of plants and animals around the world, The development of human language and culture, and even the basic structure of modern ecosystems all bear the imprint of the Ice Age world. We are, in a very real and profound sense, products of the last glacial maximum. The study of the last glacial maximum has revealed that Earth's climate system is far more dynamic, sensitive, and interconnected than was once believed. Small changes in orbital cycles, operating over thousands of years, can trigger massive shifts in ice coverage, sea level, and global temperature patterns. Ocean and atmospheric circulation patterns can reorganize rapidly when pushed past certain thresholds, creating cascading effects throughout the entire Earth system. These insights are particularly relevant as we face the climate changes of our current era. The Ice Age world shows us that climate systems can change more rapidly than we might expect, that species can be driven to extinction by environmental changes, and that human societies must be adaptable and resilient to survive in changing conditions. But it also provides reassurance and hope. It demonstrates that life is remarkably resilient, that humans are capable of extraordinary adaptation and innovation, and that even dramatic environmental changes can give rise to new forms of beauty, complexity, and wonder. The Ice Age world was not a catastrophe, but simply a different state of our planet, one that supported magnificent creatures, complex ecosystems, and sophisticated human cultures. The story of the last glacial maximum is not yet complete. The ice sheets of Greenland and Antarctica continue to respond to changing conditions, carrying within them the frozen records of ancient climates and the potential for future change. The deep ocean circulation patterns that were altered during the Ice Age are still adjusting to post glacial conditions. The species and ecosystems that emerged from the Ice Age world continue to evolve and adapt to new environmental challenges. We are, in a very real sense, still living in the aftermath of the last glacial maximum. The interglacial period we inhabit is directly shaped by the ice age that preceded it. Our coastlines, our climate patterns, our species distributions, our soil types, our river courses, and our human societies all exist as they do because of the long cold period that ended 11,000 years ago. The great ice sheets of the past have left us a planet with specific characteristics, particular patterns of ocean circulation, atmospheric chemistry, and biological diversity that are the direct result of ice age processes. Understanding this legacy is crucial for understanding how our planet works and how it might respond to future changes. Scientists continue to study ice cores drilled from the remaining ice sheets in Greenland and Antarctica, reading the frozen records of ancient climates with increasing precision and sophistication. Each layer of ice contains information about past temperatures, precipitation patterns, volcanic eruptions, atmospheric composition, and even the frequency of dust storms and forest fires from thousands of years ago. These ice core records have revealed that the transition from ice age to interglacial was far more complex and variable than previously imagined. Instead of a smooth, gradual warming, the end of the last glacial maximum was characterized by rapid oscillations between cold and warm conditions, dramatic reorganizations of atmospheric and oceanic circulation, and sudden changes that occurred over periods as short as a few decades. Understanding these rapid climate transitions is crucial for predicting how climate systems might respond to current and future changes. The Ice Age world provides us with natural experiments in climate change that occurred on scales and at rates that would be impossible to study through any other means. And perhaps, if orbital cycles continue to operate as they have for millions of years, our descendants, tens of thousands of years from now, may find themselves once again living in an ice age world. They may look back on our current warm period as we look back on the last glacial maximum. There's a different state of the planet, one that supported different forms of life and required different ways of being human. But that is a story for the deep future, written in orbital mechanics and climate feedbacks that operate on timescales far beyond human experience. Tonight, as you settle into sleep, you can rest in the knowledge that you are part of an unbroken chain of life that stretches back through the Ice Age world, through all the climate changes and environmental challenges that life on Earth has faced, back to the very beginnings of life itself, billions of years ago. You carry within your cells and your genes the legacy of ancestors who survived ice ages and mass extinctions, who adapted to changing climates and evolving ecosystems, who developed the remarkable technologies and social structures that allowed human beings to thrive in environments ranging from tropical rainforests to Arctic tundra to the mammoth steppes of the Ice Age world. Sleep well tonight, knowing that you are part of life's ongoing story of resilience, adaptation, and beauty. Dream of Ice Age landscapes populated by magnificent creatures that no longer exist, of aurora dancing in unpolluted skies with a brilliance unknown in our modern world, of human communities that lived in harmony with natural rhythms, understanding their place in the complex web of relationships that connected all living things. Dream of the long, remarkable journey that has brought us from that transformed world to the one we inhabit today. So, journey marked by countless acts of courage, innovation, and adaptation by creatures both human and non human. Dream of glaciers flowing like slow rivers of ice, of grasslands that stretched beyond every horizon, of nights so clear and dark that the Milky Way cast shadows on the ground. The last glacial maximum reminds us that our planet is far more dynamic, mysterious, and capable of transformation than our brief human lifespans might suggest. It shows us that Earth is capable of supporting forms of life and landscapes so different from our current experience that they seem almost alien, yet they are all part of the same ongoing story of which we are now the temporary protagonists. As you drift off to sleep, imagine yourself connected to all those Ice Age ancestors, to the humans who painted by lamplight in deep caves, to the woolly mammoths who shaped entire ecosystems through their daily activities, to the cave lions whose roars echoed across frozen grasslands, to the glaciers themselves, those slow moving rivers of ice that carved the landscapes we call home. You are part of an unbroken web of life that has persisted through ice ages and warm periods, through mass extinctions and evolutionary radiations, through all the dramatic changes that have shaped our planet over deep time. This web connects you not just to your human ancestors, but to every living thing that has ever existed on Earth. Rest well, sleep peacefully, and may your dreams be filled with wonder at the remarkable ongoing story of life on our extraordinary planet. May you wake tomorrow with a deeper appreciation for the incredible journey that life has taken, the challenges it has overcome, and the beauty it has created along the way. Good night, wherever you are in the world. Thank you for joining me on this journey through Ice Age time, through landscapes that no longer exist, and stories written in stone, ice, and DNA. Sweet dreams, and may you always carry with you a sense of wonder at the magnificent planet we are privileged to call home.